In this video, we're going to look at a really fun part of probability, and that's just all of the different applications or the different ways that it can be presented to us. So one way that we were introduced to in grade 9 and we build on now in grade 12 is this thing of contingency tables. So basically you've got two factors. You've got school A and school B, and then you compare that with watching TV or not watching TV. So here's one factor, here's another factor. Two-way contingency table. A survey was conducted among 60 learners at school A and 100 learners at school B to determine how many of them watched TV when they got home from school. So here we've got a partially completed table. Then it says here, number 1, calculate the values of X and Y. So some things are missing here. And then, are the events, school A and did not watch TV, mutually exclusive? So what they're doing is they're taking a concept that we learned years ago and they're combining it with some of our matric and even grade 11 probability theory. So let's start and complete this table. The first thing that I want to do is just read the question. It says a survey was conducted among 100 learners at school A and 60 learners at school B. So that's very helpful to know because that actually tells me what the totals are of each of these columns. So then, or each of these rows. In school A, we had 100 learners, and in school B, we had 60 learners. And that would make sense to say 100 plus 60 gives me the overall total there, 160 learners. Okay, now to calculate X, I've got two options. I can either say 80 plus X equals 100, or I can take the did not watch TV and say X plus 12 equals 32. And either way, if you look at that, you will see that X is equal to 20 because 80 plus 20 is 100, 20 plus 12 is equal to 32. All right, and then similarly, I can work out the missing Y by using the info that I've got. So students who watched TV, there are 80 here and 48 here, so 128 in total. And I can check that answer by saying 128 plus 32 does give me 160. So there we go, the answers for X and Y. Now they ask me, are the events school A and did not watch TV mutually exclusive? Okay, so let's just have a look. School A and did not watch TV. So my eyes are on this block here. Okay, what do I know about mutually exclusive events? If events are mutually exclusive, it means the intersection, the AND part of the probability is equal to 0. Okay, so let's work out then. What is the probability that a student goes to school A and does not watch TV? Okay, what do? We take the number of students listed there, 20, and we divide it by the total number of students, 160. Okay, we can give that answer in simplified fraction form, so 1 over 8. And then we can say to our marker, well, that is not equal to 0, and therefore they are not mutually exclusive. And so there we have it. It really is a straightforward way of looking at probability. And as long as you understand that each column has a total, each row has a total, and then remember to use the overall total when working out probabilities. Now let's look at probability trees. So I've chosen a nice tricky example here to get you thinking. It says a bag contains 3 green sweets and X pink sweets. So we don't know how many, but at least we've got an X to work with. 2 sweets are randomly pulled from the bag without replacement. What is the probability of selecting 1 pink and 1 green sweet? Okay, now the minute that I see this wording here, without replacement, I know that I'm working with dependent events. And when I work with dependent events, probability trees are my best bet. Because what's going to happen is I'm going to take out 1 sweet and eat it. And that's going to affect the number of sweets in the bag. And so a probability tree just helps me to keep track of exactly how that goes down. All right, so what I'm doing is I'm choosing 2 sweets. So I've got 2 events, sweet 1 and sweet 2. When selecting sweet 1, I can either choose a green sweet or a pink sweet. So green or pink. Okay. And then when selecting again, I can either choose green or pink, green or pink. Okay. Now I need to try and fill in the probabilities along this tree. Okay. I've got 3 green sweets. So in round 1, 3 out of the total number of sweets. Okay, and we don't know what that is. That's why I told you I've got you a thinker here. 3 plus x. Okay, we don't know how many pink sweets there are, so it could be anything. But that's okay. Then down here I can choose x pink sweets out of, again, the total number of sweets. 3 plus x. Okay, now what's going to happen is in the second batch of branches, I'm definitely going to have fewer sweets. So I'm going to then say this is going to be 2 plus x, because I know no matter what color sweet I chose here, I'm going to have eaten it and I'm going to have 1 less sweet. So just 3 plus x minus 1 is going to give me the 2 plus x that I'm going to use in my denominator for the rest of this question. 2 plus x, 2 plus x. Okay. Now we have to think about these numerators. If I ate a green sweet, then there are no longer 3, there are 2 green sweets. Okay? And if I ate a green sweet here, then the probability of choosing pink, all the pink sweets are still there. So there are still x pink sweets because I've eaten a green sweet. Okay? Now on the next one, I've eaten a pink sweet, which means all 3 greens are still available. But I've got 1 fewer pink sweets, so x minus 1. Okay, a nice challenge here to get us really thinking. Now they asked us, what is the probability of selecting 1 pink and 1 green sweet? Okay, now what really helps me is just to list the outcomes. So I'll follow my branches, green, 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 pink, pink, green, pink, pink. Okay, and that's going to help me just to keep track of what went down on this probability tree. Green, pink, pink, green, and pink, pink. Okay, what's the probability of selecting 1 and 1? And essentially the question should even say in any order, but it's okay. We understand what they mean. Basically, we need to have 2 options. So how do we do this? Remember that when you travel down the branches of a probability tree, you multiply and then you add all of these together at the end of the day. Okay, so I'm going to follow my first batch of branches that satisfies, and I'm going to say, okay, well, the probability of 1 and 1 there, probability 1 green and 1 pink is equal to, and we're going to say this is 3 over x plus 3, or 3 plus x, and then multiplied by x over x plus 2. Okay, and then we're going to follow the other branches that yield a satisfying solution, and that's those 2. So plus, I'm going to need to go onto another line here. Let me see if I can space this out. Okay, plus, then we've got x over x plus 3 multiplied by x minus 1 over x plus 2. So there is our probability, and then just depending on the teacher and the instructions they've given you, you would need to answer the question. Okay, I can see that there's a common denominator here, so we're just going to use some algebra to finish this off. So what we can do is we can say, well, then the overall denominator is going to be x plus 3, x plus 2. And then in our numerators, we're going to multiply. So 3 times x is going to give us 3x, and on the other side here we've got x times x minus 1, so that's going to give us plus x squared, x times x, and then x times minus 1 minus x. So now we end up with x squared, and then 3x minus x is plus 2x over this denominator, and I'm almost certain that any teacher would be happy for you to leave it in that form, but if you wanted to, you could even multiply that out. Okay, probability trees, hugely helpful when it comes to without replacement questions, and as long as your foundations are good, remembering that if you've eaten one sweet, you need to have one less option, then you should be able to answer any question that comes your way. And then finally, Venn diagrams. This is probably my favorite section of probability. It says here there are 300 learners in a school. 60 of these learners sing in the choir, 220 play sport, and 25 sing in the choir and play sport. Are the two events independent? So independent, just to refresh my memory, means the probability A and B must equal to the probability A times by the probability of B. So if I can prove that, then it is independent, or then they are independent of each other. If I can't prove that, then they are not independent of each other. Okay, but in order to do that, I need to put together a Venn diagram, because that's going to help me find these different probabilities. So we've got 300 learners in the school. So NS is 300. 60 sing in the choir, 220 play sport. We're going to have to call one of these choir and one of these sport. 25 do both. So 25 sing and play sport. Okay. Now, if they say to me 60 sing in the choir, then I can simply say, well, if this total circle needs to be 60, then 60 minus 25 will give me the 35 who only sing in the choir. Okay? And then 220 play sport. So 220 is what this entire circle needs to add up to, but 25 of them are already there, so that leaves us with 195 left there in the sport circle. Okay, but there might be some students who don't do any of the above because they're 300. So let's say 300 on the calculator minus the 35 who only sing in the choir, minus the 25 who do both, minus the 195 who play sport. That leaves us with 45 students outside who neither sing in the choir nor play sport. Okay, and once we've got this, answering the questions becomes a dream. Question 1, are these two events independent? Okay, let's work out what is the probability that you sing in the choir and play sport. So that's this intersection here in the middle, and there are 25 learners who meet that criteria out of the 300. And we can simplify that to 1 over 12. Then in a separate calculation, so we can't combine them yet. Our goal is not to solve an equation here. We are literally proving, is this equal to this? Then the events are independent. So in a separate calculation, what is the probability that you sing in the choir multiplied by the probability that you play sport? So we're going to work that out. The choir is the whole circle, hey? And so that's 60 out of the 300 learners multiplied by the sport, that's 220 out of the 300 learners. So now we're going to work that out on the calculator. So 60 over 300 multiplied by 220 over 300 gives us a probability here of 11 over 75. And so now we can conclude these are not independent because the probability of choir and sport does not equal the probability of choir multiplied by the probability of sport. Okay, a nice grade 12 question there mixed in with the Venn diagram. Then, what is the probability that a randomly selected learner does not play sport? Okay, so probability, sport, complement. That means not sport over there. Now, there are two ways that we can work it out. We can either just say, well, these ones don't play sport and these ones don't play sport. So it's the combination there. Or we can be fancy and we can say not also has this equation, 1 minus the probability of actually playing sport. And either way, you'll end up at the same answer. So let's do this version here. Probability of 1 minus. We know 220 learners play sport. So 220 over 300. And so that gives us a probability there of 80 over 300, which simplifies to 4 over 15. And then finally, again, the Venn diagram helping us out so much here. What is the probability that a randomly selected learner neither sings in the choir nor plays sport. And so over here, we have determined that 45 students are out there. They are not in either of those events that's taking place. So 3, probability, neither choir nor sport is simply going to be those 45 out of the 300, and that simplifies to 3/20. And there you have it. Venn diagrams, hugely helpful when it comes to answering probability questions, because it helps us just to picture the intersections, those who don't belong, and even to work out students who only sang in the choir but didn't play sport. There they are, and it's straightforward. We can jump straight into the probability answers just by using this diagram.